So for tonight, we've got two presentations as usual. Chris Blasco. Chris Blasco is going to tell us about some of his work on computer vision, and Nathan Fish is going to give us some information background on his experiences with system D. Both, I think, will be very interesting. So as I was starting to allude to, we have a good number of presentations stacked up. So I can say some of them. We have DAL and SSL next month. We have a DASKey and USB over IP the month after that.
I still love to do the DASKey presentation, but I don't know if it'll be available on that.
Okay.
So you said there's one starting now?
March 2nd.
Can I switch now?
Yes.
Probably.
Did you want to switch earlier? You want to do this an introduction?
I could do something in January.
I wouldn't mind switching. Where are you right now?
I'm in February.
Yeah, I wouldn't mind going to February. It gives me a bit more time.
All right, I will do January.
All right. So you're ready. So you go to February and then do January?
Yeah.
All right.
And to that end, if anybody has any tasks with audio that they would like to do, so I can tailor some demos for things that people might actually be quite useful. I do lots of stuff with audio, but some is a little niche. So if there's anything you want to be able to do, as well as getting recorded audio and manipulating it, just send me a message, and I will do it and show you how to do it.
I can
Cool. Yeah, it's not so much a file. I'll probably create most things on the fly. But yeah, it's something that you want to learn how to do.
How do we reach you?
The daily lessons.
Okay.
Check that. I'll put a post in that video. I'll give you the address.
Cool. Yeah.
Okay, so rearrangement on the fly. So we still do need for March. Nikolai is going to do a presentation on Soul, so we need something to go with that. So I assume that's going to be
Is there something called Pepper? Is there a software project called Pepper?
No funny names. Small fun and games until your project gets popular. Then it's embarrassing. Or is your, I don't know if your project is yours beginners or advanced?
It's as usual, like how I approach all of the admin tasks from the beginner perspective, because I led them myself, and the thing is like the easiest things that you can learn, or the most easiest perspective on the tooling. So it's like,
But still more, you actually want to admit your system. So I think like more user or an end user focused presentation would probably pair well. Maybe I guess it doesn't matter. Okay, either way.
yeah,
If
my
you would-
developers are end users of my classes.
That's true.
It's,
If you have a presentation you would like to do either, so we've been structuring for sort of one that's sort of user focused, more end user, you don't have to have as much background, and one that's more advanced. Or you can make trouble like Nikolai and, be kind of happy between. So if you're interested, so that's March, let us know on the mailing list, or I can do what Paul gets me to do. Does anybody have a presentation they want to do right now?
Not right now.
Oh, right, no, in a few months.
Yeah, probably. Yeah, probably exploring jellyfin. Yeah, jellyfin is it's like a Plex alternative. It's completely open source. It's a fork of Envy before they went closed.
Cool, that would be very interesting. All right, you want to talk after the presentation?
Absolutely, yeah. It's only my third day in Kitchener, so very happy.
Welcome. We're happy to get you, trying to get you presented. Awesome. All right, so the other ones, so April, we've got latex at the law library and cluster SIG, and then May on, a million years in the future, we'll need more presentations, so I'll bother you all next week. Other events, the Libre Planet satellite meeting that Stephen Paul Weber is trying to organize. He sent out a post for people to buy tickets. I still haven't done it because I keep forgetting to go back into my email, but I'm going to do that. I encourage you to do it too. I'm assuming getting payment for tickets up front will probably make it easier for him to book things and plan stuff. So if you're interested at all,
which one?
Zebra Planet, they call it satellite, because it's, Zebra Planet is in Boston, I think.
Yeah, the main one is in Boston.
Yeah, and I guess they're having a system where they run other smaller events at the same time that they're calling satellites, and Stephen wants to organize one. And I really should know what date that is now, but I don't. In the future. And Mark was going to
Well,
announce.
actually, to that point, I'm with the KW Linux event that happened 2 years ago.
Yes.
And so we're probably going to revive that, and we're working on that. And I think Liver Planet, we may try to get together with them and try to coordinate with them.
You have around time
No, we
frame?
don't have a date yet.
Well, do you have a mailing list that people should join that you might post to our mailing list? If anybody wants to help out?
How about I'll post it on the KWLUG list, and then from there, work from there.
Okay.
Yeah.
And Mark has other
And
stuff?
the other one is that Bob Luffman has a VoIP group, and they normally have a social in December, and so I normally go to it, and then I'm also on the KW and PSA nonprofit system admin group, and we normally join him as well, and I'm also on the Liberal Office Waterloo community group, and we're three here, and we thought we could also join them as well, and we're wondering if KWLUG would like to join, just to make it, a lot of the faces, we're all the same, like we go from one group to the next, and it's always, a lot of us, we see each other, and you just suggested that maybe the
Python group.
Python group.
Like I can announce in the KW Ruby group as well.
yeah, and if we could find like a common date and have a social somewhere at a restaurant and just, and just get to meet each other, it's kind of good to get to know each other, So, how about if, I can coordinate and get all the names and, reserve at a restaurant, and out of this should come up like a date that's a little common for everyone, and we can try to, have a social then and see how that works out. Okay?
Or you should just pick a date.
Yeah.
Oh, okay.
Or maybe
Don't try and ask people what date
Well-
works for them.
Whatever date you
Ask
want.
everybody, and then fix the date.
What you can do is you can see when the different groups are meeting.
Yes.
And either hold it on one of those dates or not hold it on one of those dates. And then just pick the date, because some people will be able to come and some people won't, right?
Yeah.
I'm gonna keep my promotion hat on.
Paul, how would he look up to find out what groups are meeting on any particular day?
You go to kw-dashboard.com. Oh, no,
Damn it.
wrong one.
No, not yet. So WattCamp is a site that Paul helps to maintain that collects approximately all of the tech-focused events in the region. So, for example, for someone who is brand new to the area, wattcamp.org would be very helpful if you're looking for new places to go out and see things. There is something happening almost every single night. Some of it tends to more academic side of things, some of it tends to more businessy side of things. Some of it's user groupy kind of stuff, but there's a whole variety, and we've joked that you could probably have pizza almost every single night if you didn't want to pay for dinner. It'd probably not be very healthy, but you cut down on your costs. All right, I think that's it. Oh, one thing I meant to mention, Marcel Gagne, who's a local Linux person, has also started a new podcast called TikTok. It's something like that. It is weirdly like the social media, the social network. So I will post a link to that. I've listened to one or two of them. They seem good. It's interesting chit-chatting about Linux and free software kind of stuff. All right. Unless anybody else has anything else they need to announce, I'm going to pass over to Chris. And we're going to turn off the lights. So I'm going to turn it off, but let me know if
For a company specialized in object recognition. So I'm not a researcher. I'm not someone that works at Google that actually develops deep learning architectures or anything like that. But we do make use of these technologies for our purposes. Also, at any point, if you have a question, just shout it out, put up your hand, whatever. I want this to be very informal, very interactive, because I'm sure a lot of people have questions. My first few slides here are going to be very basic as basically how pictures work on computers, what pixels are, etc., just so that everyone has a common ground so that you can understand what I'm talking about later. Oops. So, what is computer vision? Computer vision is just the process of taking input, doing some sort of pre-processing, getting features out of the image, making a decision on that data, and then performing an action. So we could have regular photos, a video stream or from a video file, or some input such as radar or LiDAR from a self-driving car. Then we want to take that information, normalize it so that there is a common format going into the pipeline. Then we do things like find edges, find contours, find textures, etc. Then we start making decisions, is this a cat, is this a dog, a person, etc., etc. Then we do something such as notify a user, perform an action such as if it's someone jumping in front of the car, a self-driving car, the car can stop, or we can have access control, or we can just log the data, etc. So pixels, I mean, I'm sure everyone knows here how pixels work, but just a basic primer, that is a higher resolution photo. We have a lower resolution photo just so that you can see how the image is actually comprised of small individual units. How displays work, how our eyes actually see images. Displays work on the basic principle of having 3 color channels, red, green, and blue. And these are different configurations for different kinds of displays. And that's essentially how the data is stored. It's stored in 3 separate color channels on a basic level. There are, of course, a huge variety on how this is actually accomplished on a digital level. But the basics are there are 3 8-bit channels, red, green, blue. Sometimes a 4th one for alpha, for transparency. And that's the basics of it.
What is size normalization? Will you get into that?
Sure. Size normalization is so 900 by 600. I just chose that resolution as more of it's a very random example, but normally you would have, let's say 1920 by 1080, a 1080p video coming in. You want to normalize that down to something smaller because object recognition almost never happens on higher resolutions. It's usually scaled down to a common size, usually around 300 by 300 or 1000 by 1000, something like that. But if you have random images being put in, so think of Google image search. When you search for cats, you get 10 million photos of cats. In the past, this was usually aggregated from metadata that was posted on the actual website. But now Google uses machine learning algorithms to find what photos have cats in them. And you're going to have a huge variety of photos, everything from very high resolution DSLR photos to really small thumbnails. And that is the size normalization, where the pipeline will take whatever size photo and it will normalize it into a common pipeline. So basically think of it as a funnel. Large or small, it's going to bring it all in, and it's going to be single size for the system to use.
So for self-driving vehicles, what is the normal size? I mean, what detail they go through? You know, if you go on the road and there is a small rock, if you normalize too low, it can be recognized, or?
Oh, that's a very good question. One of the biggest challenges for object recognition is small objects. The smaller the object, because put it this way, this is a very, very low resolution photo, 42 by 35. But you can imagine in this photo, a rock that would be, you know, let's say this size, which would be a problem for a car, any car. In this photo, it's going to be basically 1 or 2 pixels. There is virtually no information there for it to work with. It's not going to know if it's, you know, part of somebody's eye or if it's a photo or a rock or an animal. It's not going to know, right? So that is a challenge. For self-driving cars, I wouldn't be able to speak to that because I don't work with that directly. But self-driving cars usually use like radar, LiDAR, as well as a whole battery of cameras around the whole vehicle. So there usually is some overlap compensation for basically to not miss something. That's basically it. Any more questions?
So to handle something like that, could you, instead of resizing the image, would you crop or take a section of the image and use it?
So, okay, you're
Is
getting
that
into
part of
you're-
size normalization?
Yeah, you're getting into something that actually is part of modern efforts to basically combat that. There are multi-stage approaches to doing that sort of thing. Now, it's not impossible. You could feed, actually there is a, I can't remember the name of it. There is a project that has a neural network that can take in 16,000 by 16,000 satellite photos to look for boats, cars, whatever on the ocean or shorelines and that sort of thing. And it's completely possible to do that. The larger your image, the exponentially slower your process is going to be executed, right? For self-driving cars, it's really important because you want to have real-time execution, right? You want to have under 100 millisecond response time for anything. So there is a trade-off there for accuracy versus speed. And again, that's another common problem with these systems.
And for format conversion, it's the same thing. Self-driving cars are specific, have specific format compared with other types of applications.
Well, self-driving cars are much more specialized. NVIDIA makes actually a specialized module for that. Tesla made their own system. It's basically an embedded system. That's all it does. It just does all the object detection and all that stuff on a single board, very fast. But their whole pipeline is going to be optimized. They don't have to worry about users uploading an image. Like there was a little while ago, there was a website you could upload your own photo to, or photo of anyone really, and it'll spit out which celebrity you look most like, right? And that's in that instance, you want to be able to handle JPEGs, TIFFs, bitmaps, PNGs, WebP. For a self-driving car, that wouldn't be an issue because the pipeline, the input would already be optimized for the input from the camera, etc. So that wouldn't be a concern there. Anyone else?
So the idea of format conversion, each type of application has specific format that all the input have to convert to, yeah? Or is that true?
Yeah, it really depends on the framework also. A lot of the newer frameworks like Google's TensorFlow will actually handle its own input on its own. So you could feed in JPEGs, bitmaps, etc., and it will do the conversion for you. So you could just feed it the images and it'll do the thing in the background. Other frameworks, or if you're building your own pipeline, such as using OpenCV, you want to make sure that you're using the same format when you're actually doing your processing of the data. It just makes it simpler for you as a developer. That's all. Anyone else? Okay.
You keep going.
Yeah. So yeah, this is just where I was at before. This is just a raw representation of grayscale image showing raw values of an 8-bit pixel. So 0 being black, 255 being pure white. And then naturally how color photo is actually broken up into the 3 color channels, and those color channels can each be represented by their own grayscales. All right, so this is what I was talking about before about the pre-processing. So color format conversion, the funny thing is with OpenCV, it was originally developed by Intel, and then it became a open source project. And it pretty much is the gold standard for just about anything involving computer vision or image input to deep learning frameworks, etc. You're almost always going to find OpenCV somewhere in the pipeline. But the weird thing about it is that it's the odd duck out of everything. Normally, things are stored in RGB format, red, green, blue. OpenCV loves to use VGR, blue, green, red, by default, so there often has to be a conversion when you have image inputted. You have to convert it to VGR in order to do what you want to do. And on top of that, if you actually are doing some sort of processing, looking for contours, edges, textures, or feeding it into a deep learning network, you're often going to use grayscale, because grayscale has all the information you're going to want to have for shape. You're not really too concerned about the color of a cat or the color of a dog, unless you are looking for maybe a breed or something specific. But if you just want to know it's a cat, dog, car, you don't care about the color. And working with grayscale is going to be significantly faster than working with color images. So then we have the resizing. Image rotation and histogram normalization is very important for data augmentation. You have a deep learning network, you want to train it to look for a person, or let's say you want to look for a car. Sourcing images, you might think is easy. Get a couple thousand images on a good weekend. But realistically, if you really want to train a network to be very accurate, you want in the hundreds of thousands of images to feed into the network, at the minimum. And this is where data augmentation comes into play. The system doesn't care if it's essentially the same photo, cropped, transformed, rotated. To the system, it's a different object, it's a different photo. So you can take a data set of, let's say you spent a good week sourcing images, doing the labeling, boxing everything out manually, and you have about, let's say, 20,000 images. You can expand that to a much larger data set, to about 50,000, simply with data augmentation. And you can take your accuracy from, let's say, 95% and bump it up to 98, 99%, and get an accuracy that you're looking for. So you would do that with like a whole combination of stuff. Rotation, flipping, you can even skew the image so that the perspective looks a little bit different. You would resize the image, etc. It's almost invaluable for deep learning networks. So I'll just show you a couple very basic things that you can do with pure OpenCV. Let's see here. So here's a simple, very basic image of blocks on a white background. Using just OpenCV, we can count how many objects we have on the screen. I'll show you the code in a minute. So what this code, I'll show you the code in a second, but what it's doing is it's applying a threshold limit. Well, first it's converting it to grayscale. Then it's applying a threshold limiter, basically saying anything that is colorful or has some sort of greater than 0 value, it's going to normalize it all the way up to a flat level. So everything that has some sort of color, it's being shot up to 255, and everything else is just being dropped down to 0. Then it boxes everything out by looking for contours. And this is all built-in stuff within OpenCV. You wouldn't have to do any of this manually. Then we loop through all the instances that OpenCV finds for the contours, and we can actually count how many objects there are. So here, every time I hit enter, you can see a new box appear around each object. And we have 10 objects found. Very simple. And I'll show you the code here now. So this is just argument parser where I tell it which image I want to look for. This is OpenCV's basic image input reader. Then we just call an OpenCV function to convert this color into, this picture into a color to grayscale image. We store the value here. We add a slight blur. because there's always going to be small little artifacts around the edges, and that can be picked up as, if you have a small grouping of pixels off to the side from a large object, that can actually get picked up as smaller little individual objects. To get around that, we apply a slight blur to the whole image that smooths the edges, so we get a solid object instead of these disparate little parts. And I can actually show you what that looks like if I don't apply the blur. But from there, this is where we apply the threshold. So we tell it which light values we want to cut off at, so we can create a sharp separation between the plane background and the sort of object. And this is OpenCV's fine contours method, where we're going to store all of the contours finds in the object. And then here we just loop through them, draw our contours, and show each result on the screen. And then based on how many we found, we just output the image or the text right there. So if I turn off this blur, actually this image might be clean enough that it you might not see it here actually. Okay, let me use a different photo. Whoops. I have it set to listen to the Q key for quit. If I close the box, Python just gets stuck in memory. So I got to get it. Actually, I'll show you again. There are some other stuff running in the system that actually is running on Python too, so I don't want to do that.
Only the first time.
Nice try.
You do kill all space X F. That's a full command line.
So this was that colorful photo that I just showed you a second ago. You can see how you can get odd results if you don't apply a blur. Actually, I'll show you the block one again. So this is that block image. Now I'll adjust the threshold here to something that shouldn't work. So there you go. It's applying the cutoff at an odd point. That's another result that we do want. Try to actually make this do what it shouldn't do. So this is a good example. Because of the colors, each color is going to have a different intensity. And with this, if I were to run the counting function on this, it would tell me I have 4 objects, because it's going to count those 2 edge pieces there. It's going to count those as separate objects. Does anybody have any questions on this? This is like really simple. Yeah.
For original picture, the color one, is data augmentation somewhere hidden in those functions that you call?
No. This is pure OpenCV functions. It's just like I'm not going to pretend to know the ins and outs of all the math going on behind it, but this is stuff that's been around for quite a while. It's considered basic compared to other stuff that we have now. I'm actually going to skip some of the other demos that I had here because I want to get to some of the more interesting stuff with time. Does anybody have any more questions on this stuff here?
It's run on a GPU?
Nope. OpenCV, all this stuff here, it's happening like this on a CPU. You can do it on your phone in a split second. It's very, very basic.
So none of the functions we've run so far are neural networks?
Nope. This is all, I guess you could just say they're all mathematical.
So OpenCV doesn't have data augmentation over it, yeah?
Actually, OpenCV has evolved to the point where it actually has its own convolutional neural network framework. It's to the point where you can do some pretty amazing stuff with OpenCV alone. But OpenCV you would use, like for data augmentation, for your question directly, you would actually have to build out your pipeline. So you'd have to tell it, and there are many other projects out there, open source projects, that you can use for this. You can just grab them, feed it a whole bunch of images, and it's going to spit out all sorts of augmented images with the rotation, skew, resizing. It's very handy. So, high level applications of computer vision. Optical character recognition. I mean, we've seen this happen with just about everything. Google Translate now has a really neat function where you point your phone at a sign and it will translate it from one language into another. And it does this first by recognizing what the characters are. Then from there it does the whole actual translation and spitting out the result. Machine inspection. This is something that's been around for a little while too. Even some pharmaceutical companies use this for ensuring that the proper medication is being dispensed for the correct patient by using computer vision to make sure that the pills are the correct color, size, they have even like little markings on them. Retail automated checkouts. There are some stores in Japan and China where you don't even have to, like there's no cash register. You just put the stuff in your pocket and then it uses a system. I wouldn't be able to describe it perfectly. I don't know the in and out of it, but it uses machine learning and computer vision to basically see what items you are picking and putting into your bag, and it just charges it directly to your account. Medical imaging. Some really amazing stuff is happening there with cancer research, diagnoses. It's at the point now where computers are better, well, I shouldn't say better, they're faster, more accurate, and can go through more data than a doctor, and find, let's talk about cancer. They can find cancer earlier than many doctors can because it can look at huge amounts of data to learn the little things that a doctor might miss, simply because he hasn't looked at literally millions and millions of photos of CAT scans and x-rays to know what little signs, the early signs to look for. So it's helping in ways that will help people get treated quicker, earlier, so that their prognosis can be better. Image processing, we just talked about. Photoshop, there's a lot of image processing through machine learning. You probably heard of the content fill. You've probably seen that where you can just select an area, use content fill, and it fills it in the, with surrounding pixels, basically. A good example would be if you have a really nice pristine photo of like a nice landscape and you have very odd man-made objects sitting right in the middle, you can use content fill and it will automatically erase it and make it look like there was nothing there. It'll fill it trees, grass, clouds, skies, mountains. It'll do it very beautifully, and it's through these sorts of things. Self-driving cars, motion capture. Surveillance and biometrics is what I'll be able to talk about the most, so I'll just continue on and we'll get into that. Here's an example of modern object detection. This is something that would be running on a GPU. There are systems out there you could do this with a CPU, but you have to employ a few tricks in order to get it to work. But primarily you're going to do this on a GPU-based system. And right now NVIDIA is killing it. They are ahead of everyone else in terms of framework, engagement, and technology. You could basically do this on an NVIDIA Jetson Nano board. It's $120 for a dev board, and you could do 8 1080p streams at 30 frames a second. Face detection. Same idea, but face detection has its own unique sort of subset in the whole object recognition world. So with seeing faces, there are two things that you need to do, or rather, to recognize who that is, there are two things you need to do. Face detection. You have to find in the frame where that face is. You have to be able to say that that's a human face, or is that a car, or is that an animal? Then the next step is, who does that face belong to? So face detection naturally would be the first step for facial recognition. this, a good example of this would be those face swap apps you see where people are swapping their faces with, friends, or there's that one guy on YouTube, he does a lot of swaps with his baby. It's pretty funny. But photo processing such as portrait mode, so for example the iPhone has that really neat portrait mode where it'll automatically sharpen your face and kind of blur the background. There's a lot of neat tricks, but this is done with face detection because it needs to know where your face is in the image. Now, the ways to do face detection, there are probably as many techniques as there are computer science students. Quite honestly, there are just 1,000,001 different techniques. Most of them are what you can see here: knowledge-based, feature-based, and template matching. Normally, these are actually handcrafted algorithms, so it's not fed through a deep learning architecture. It's just someone designs an algorithm to look for the different features that they want to look for. Now, the appearance-based is where we get to the more sophisticated stuff, specifically neural networks. There's all these other different kinds, which I'm not even going to get into because they're interesting from a science standpoint if you're actually doing research. For the average application of facial recognition and face detection, mostly irrelevant. So I'll mention one of the most common techniques for face detection, which is not a neural network. It's called hard cascades. They've been around, I believe it was 1994 was the first time it was introduced. And this is one of those handcrafted algorithms. It's basically a filter map that describes contrast areas between, and you can use this, it doesn't have to be faces, it can be cars, bicycles, cats, whatever. But this is the general idea of how it works. So it's looking for contrast zones for the eyebrows, because a person's eyebrows are typically going to be darker than their surrounding tissue, and the eyes are going to have a different contrast, the bridge of the nose, etc., etc. So it's very fast because it's a very light process to run, but it's not very accurate for different angles. So there is a hard cascade that works great for frontal images. As soon as you turn your head, it doesn't work. So when this is used, they actually use a series of hard cascades in sequence. First they look for a frontal face, then they look for a side face, then they look for off-angle faces, etc. And it can get tedious, and there's always going to be a limitation. So another technique is called histogram of oriented gradients. It's a little similar to hard cascades, except this is more, it's not so much handcrafted as it is looking for the, I guess you could call it the direction of change for the gradients. As you can see in the arrows, that's what the actual data being stored looks for. And again, it's same limitations come into play here for angle. If you were going to box out, let's say, a car, you want to be able to detect a car with this, you're going to have to get the car from literally every angle and build a model for every single angle. Otherwise, if you only get for a few angles, as soon as you go beyond that, you're not going to see it. So I'm just going to skip past this. So I'll show you a hard cascade facial recognition model. I hope the frame is going to fit into. So right here you can see one of the limitations. Oh, I'll let Tom lights. This will work better for me because I'm standing much closer to it. So there, that's my face. If I go too far back, it's gone. It doesn't have the robustness of modern neural networks to actually see a face at a distance. So if you're going to try to use this for surveillance, you're typically going to have a camera in the far corner of the room, and it's not going to catch people coming into the room because the face is too small. So instantly it's useless. I will keep going, so we'll make sure I get as much as I can. So facial recognition. Now, if anybody has any questions here, please ask me, because this is basically bread and butter of the company. It's what I deal with a lot. But there are two basic types. There's face identification and face verification. Face identification is you're looking for a person in a sea of people, in a crowd, right? You put someone into a database. Let's just use a dystopian example here. Someone gets onto a watch list, and they're being looked for in, let's say whatever area, let's say the subway, right? There's a lot of people going through the subway. So you're doing a one-to-N look for this person. Theoretically, you could be looking at millions of faces, but you're only looking for this one. So that's face identification, because every time you see a face, you're going to grab that face. You have to generate a template or a model of that face using some sort of algorithm. And for the record, there are open source facial recognition algorithms out there, but you're going to get no more than 60-70% accuracy at best in ideal conditions. The really good stuff, it's all proprietary. So for that application, you want to have very, very, very high threshold. Basically, you want to have less than 1 in 1 million chance of producing false positive. And while it sounds like it might not be that great, that's still better than the best facial recognition human out there. There are people out there that are exceptionally good at knowing thousands upon thousands of faces and being able to say who that person is just in the snap of a finger. And these algorithms are better than the best people who can do this sort of thing. And this is the sort of thing that's used in surveillance, forensics. Police all over the world have been using this for quite a few years now. Even the Toronto police, they have a unit that's been applying this as a way to speed up investigations. And while they have gotten a lot of bad rap for it, when you really look into how they've been using it, doesn't seem to be any foul play there. What seems to be the case is that if they have an investigation that's been going on for a long time, they can't find this person, they'll then take a bunch of sources that they think this person might be involved in, run these sources through the facial recognition algorithm, and then analyze the results after the fact. And basically what it does is it puts basically a virtual eye onto the situation so that they can scan the area or the scene and make the determination. It could very well be that it produces false positives, but it doesn't matter because the officer is going to be looking at it and saying, okay, it made the identification, but that's not this person. It's irrelevant because that would never be admissible as evidence, et cetera, et cetera. So it's just a way of speeding up investigations. Face verification is different. You're doing a one-to-one match. Best use case scenario for this is face unlock on your phone. Or if you have access control systems, for entering into an area, secure facility, you're going to usually have a fob you swipe in so that the system knows you're claiming to be John Smith. So you're claiming to be John Smith. The system's going to knows that there is a John Smith record in the database. So it's now going into the database, pulling up that record, and then now comparing these two photos. So it's basically saying, are you who you claim to be? If yes, you're given access. Otherwise, it's saying that you're not. Any questions on this?
I have a question about, you showed lots of algorithms.
Yep.
So what are the criteria to choose a specific algorithm?
That is a very, very broad question, and that's the sort of thing that's still being answered by some of the smartest people in the world. It's quite honest, it's the big hot topic, big hot area of research. Like I was saying, the best of this stuff, it's all proprietary because of how fast that industry is growing. Everyone wants to keep their secrets close to the chest. So when it comes to open source stuff, you can experiment, test. I mean, you'll get good results, in a lab or in your office, using your computer, using yourself. You can have maybe 10 people in the database, and it's going to give you good results. But as soon as you extrapolate that out to a few thousand people, examining millions of faces, that error rate is going to extrapolate out to a lot of errors. So it could even come down to what your application is. If you're using like face unlock, what you have is a perfect frame of the face. You have good lighting conditions. You have a full frame, full quality, high definition photo, which is something completely different from surveillance. where you can't control it. You're going to have the camera far, far away from the subject. You can't control lighting, you can't control position. Half the time people are looking at their phones or looking down, reading something. So if you have a top-down camera with a person putting their head down, all you're seeing is the top of their head. You just get hair. You don't see the face, right? So there's a lot of considerations there.
So if you have a scene of a person running, can they adapt the algorithm? Oh, this person is running. I change the algorithm to catch a specific type of scene.
Yeah, there are body pose estimations. There's a whole bunch out there that will actually look for unusual behavior, right? So you can have an algorithm that sees that in this area, most people are usually walking. They might be gesturing a certain way, but then as soon as something becomes very vigorous, then it can kind of create an alert so that if it's a security guard, let's say it's a mall or a school or something, security guard can look like, is there a fight? Did something bad happen? Did somebody fall over? Is it someone elderly maybe is having a problem? Whatever. These things exist, right? And again, it's always going to come down to the implementation for how effective it is. So I'm going to try to power through this. AI. Actually, I'm just going to skim over this. There are two terms for the term, or two common uses for the term AI. AI in the real world is everything we've been talking about: computer vision, doing speech recognition, generating speech like Google has their deep wave voice synthesis that you hear on Google Assistant. Same thing Apple does, same thing with Siri. That is real world AI. Then you have, of course, AI in science fiction. You have Skynet, Data from Star Trek, droids from Star Wars, etc., where you actually have an artificial person thinking, the deeper meanings of life, understanding what abstract concepts are, etc. Do you guys really care about the history of? I'm going to go past this. So deep learning neural networks is where the really interesting stuff is happening. The funny thing is with deep learning networks is that we still don't really know how they work. We really do not. Google right now, they just came out with a project, huge project. It just was announced this week or last week. And the whole point of it is to give data scientists better insight to what's happening inside the deep layers, because we still have genuinely no idea. Another paper came out just yesterday that talks about, and this is from a mathematical physics standpoint, why deep learning frameworks work, because on I'll try to summarize it, I'm not going to pretend like I understood it, but basically the possibilities for the different decisions that a deep learning framework can do should be so exponentially large that theoretically they shouldn't work. But apparently now there is a theory in physics in terms of like the origin of the universe and how quantum mechanics works and all that, basically describing there is a physical explanation for why deep learning networks work, and apparently it ties very closely back to how our own brains work, which is really neat, but I'm not going to go too much into this. Three-body problem, I don't know if you guys have ever heard of this before. Huge problem in physics, where it seems like it would be simple to figure out, but it's actually not. It's really hard to do. One of the best systems right now, it's called Brutus, can solve an easy problem within a few minutes. A new deep learning network is able to do it in less than a second, which is significant. It's huge. I'm just going to go past this. You guys can ask me about this stuff afterwards. Here's an example of a very simple network. These networks do exist. You can build one on your own. And it takes, the input can be whatever you want it to be. It can be pixels in an image. It could be the frequencies in a waveform in a sound file, or data points from some experiment that was done. You do things with it at the hidden layers, and then it spits out your output. Down here is a more complex network. And I would like to point out that this complex network in this graph here is still technically a very, very simple network. This is 3 hidden layers. Some of the best networks out there have over 100, if not more, hidden layers. And again, we don't really know what's going on inside of it. Just gonna skip back through this. So this is a 3D visualization someone built on a fairly straightforward neural network called Perceptron using the MNIST data set, which is quite simply just a series of hand-drawn numbers, 0 to 9, that's it. And the whole, it's basically used as like a hello world type of data set for deep learning and visual recognition for building a network that can recognize hand-drawn characters. So you can see the input here, so those blocks would literally be the pixels, and you have all these different layers in the neural activations, and they do a bunch of really interesting stuff, and they spit out a result at the end. This GIF is a little bit shortened, didn't want to make it too long, but this is just to give you sort of a visual idea on what's happening. So combining deep learning stuff with facial recognition, we can do really neat stuff. You guys probably heard of deepfakes. There's a few YouTube channels out there that do some really funny things with it. This is also one of the things where it can actually be really, really scary, because you can actually take, you can have it set up with a good actor, take a bunch of photos and videos of someone like the president, and use deepfakes to basically paste their face onto the actor's face and produce some pretty scary stuff. Like Nick Offerman on a being. Right. Anyways, YOLO. You only look once. It's probably one of the more interesting frameworks out there. One of the best out there. And what's really neat is that the person who built it with a completely open license. He actually has a few different variations listed on the website, and it basically says you just do whatever you want with it. Here it is. Build Skynet, or make something that can watch for cats. It doesn't matter. Do whatever you want. What makes it really interesting is that a lot of the other networks, they use what's called a sliding window, where you break up the image into smaller groupings of pixels, and you check every segment for whatever you're looking for, and you keep going. And it's not that you go 8 by 8, then 8 by 8. It's you start at 8 by 8, but then you shift only 1 pixel, and then shift 1 pixel again, shift 1 pixel again. You're scanning the whole frame, basically kind of like you can think of like a scan line going through it. And while it's fast for a computer, you got to do this for thousands of lines, 30 times a second, for however many video streams you have coming in. So if you could think of a self-driving car, you're going to have like several cameras just looking at the front alone. So it's a lot of data to rip through. YOLO does what's called, there are other networks too. It's called single shot detector, or I think it was called something else here. I didn't put it down. But what it does is it breaks up the image and sort of does a simultaneous calculation on the whole thing. Pardon me. Excuse me. And what it does is it evaluates how similar each group is related to the one next to it. So it builds this map of where these singular objects might be. Then it simultaneously runs it through a classifier, giving you what your object would be. So in this top photo here, you're going to have a whole bunch of bounding boxes that are generated for the object. You have the IOU, the interest of union, where you're going to collapse all the bounding boxes for that object into a single object, so you have a clean output, and that's it. It's a very straightforward process, and I'll show you what it looks like. Sorry, when I did it before, I was using just the webcam here. Just set up this here. So this network uses over 100 layers. So you can already see here, let me turn on the lights. If you don't mind, I'm just going to rip it around the crowd here. there's all of you.
There's one lifter.
Right, it's gonna, like, put it down here. It sees laptop, keyboard. You're gonna get a couple of false detections in there, but you can see here this comes up sometimes as a remote, but that's because the threshold right now is set very low. If you noticed, it was around 20%. It's saying 20% confidence that that's a remote, but now it's coming up as a water bottle at a much higher level. Yeah, you should see that.
Laptop, or did it get home?
It should.
Well,
Yeah, it's yeah. And this is just using.
Oh yeah, it's too noisy down there.
Yeah, if you pull it up high.
Oh,
Yeah.
yeah.
Yeah, I mean this is basically it. Like this is completely, and this is using the basic it's called the pre-trained weights. So someone had taken the a large data set. Oh, sorry, you have a question? Oh, you're just playing. No problem. Someone had taken a large data set of photos. I think this one was built on what's called COCO, common object something. I honestly can't remember. It has 80 objects pre-labeled. You could download the data set yourself. There's another one called Open Images that Google put together. And when I say it's a lot of images, just the text file for the URLs for where all the photos is about 5 gigs. So it's split up into several, and I mean like, I think it's 9 or 10 separate groupings of 56 gigabytes. It's a lot of photos. Training something like that would be a difficult task. If you were just going to use a basic GPU to train the weights to actually generate the model, it would take you probably a month. But you can split that up, or reduce the speed, increase the speed, reduce the time by using multiple GPUs and cramming them together into a single unit. There's a lot of stuff going on there now.
And I have expected when I held up the Diet Coke bottle, it changed from person.
It changed from person to what?
To my name.
Oh.
So why is it ignoring the background and posters on the wall?
So this, you know what? Let me pull up the.
This is why it's not trying to get objects within the tool.
You get no person. It's in person.
It wasn't picking any.
I think it's
I'll show you
code.names.
all of this. Pardon?
Names in the last folder.
I can't see here. No. So these are the objects that this current model has been trained to look for. Everything else it should be ignoring. There are always going to be false positives. No system is 100%.
Can you turn the camera?
Turn it this way?
Poster with the large gentleman there.
Oh, yeah.
Poster on the right.
Yeah, that should work.
Where's mine with it?
Just get up there.
Okay. Me this off for a second. Okay.
And what is it?
That is really cool.
TV monitor. It's monitor, right? Even if I put my arm out, it knows that this is an arm of a person. And again, like when I say a lot of photos, I mean a ridiculous amount of photos. I actually had to get a really high-speed NVMe drive just to be able to parse through the sheer volume of photos I had. So regular 4 terabyte hard drive that I had, Seagate, it was just so slow. I would wait hours just to get a result on how many objects I'm looking at. Is the labeling is actually kept in XML format and that sort of thing. So, yeah. So does anybody have any?
What if a person doesn't want to be labeled a person? What if they want to be labeled a cat?
You're gonna have to take that up with the computer, man.
So you have to try to move the right way.
Absolutely.
How? Like simple, not like have
So-
to really know what I'm doing. Just strictly run a couple of commands. to have
There is
that.
one cat. I'm way over time, aren't I?
Pretty close, but
Do I have 5 minutes?
sure.
Okay. So I will give you a more detailed explanation after, but I'll give you a high level. So three things you need. GPU, pretty much anything 9 series onwards from NVIDIA should do it for you. The newer and the faster, the better. You need OpenCV, which is should be compiled with GPU, and it's called CUDA. No, well, yes, it's the CUDA framework, but it's the CUDA. I'm drawing a blank. It's the CUDA neural network. It's the CUDNN framework. It's an additional framework on top of CUDA. And compiling OpenCV with that stuff is very much a pain, really a pain, honestly. But once you get past that, then all you have to do is compile Darknet, which is the YOLO framework, which is pretty straightforward. You just download it from the author's GitHub page. Download it, literally type make, or you have to go and make sure you enable, CUDA and all that. Hit make, compiles, and then on the GitHub page, it gives you all the examples what you need to actually run with photos, a video, webcam, whatever you want, and you'll get exactly this. And then if you want to go beyond that, you can then use the pre-trained weights as a jumping off point. Add in your own photos to essentially use that existing model to train your own model so that you can now detect whatever you want. Absolutely whatever. Yep.
What if I'm freedom loving and only have AMD cards?
Sorry, what?
What if I'm freedom loving and only have AMD cards?
This is where NVIDIA really cornered the market. They came, first of all, CUDA was their first bullseye, because it really was a really simple way for developers to tap into this stuff and really start playing with this accelerated computation. Then from there, they really started engaging heavily with companies. Like I myself, I have my own contact at, not to sound like I'm like super hotshot, no, it's just, they literally do this with every company. I have my own direct contact at NVIDIA. I have a problem that I'm running into. I email this guy saying, this is the problem I'm seeing. He says, okay, let me contact my engineers. And I hear back from them within a day, and I have like a solution from NVIDIA for my problem running on their hardware. And they do this because they really want to have that engagement with companies. They really want to lock you in on their ecosystem and their hardware. And it has worked 100%. Right now, you want to do anything serious with deep learning and object detection and all that, you're using NVIDIA. So I have one more demo that I want to show you.
Windows 2.
Yeah, so actually, yeah, you can see the output here. It spits out the values into the command line, but that's useful for us right now. I'm going to skip over the facial recognition stuff because I'm pretty sure that's pretty basic. Everyone's seen that before. Anyways, yeah, thanks for your time, everyone.
We'll take a quick 5-minute break. The thing I always forget is we usually go to dinner afterwards.